Okay, good afternoon. We will continue today with evaporation processes, measurements, calculation methods. Then we move on to other topics. Last lecture, we went quite into detail about the coupled water and energy balance, and we went into the main processes of evaporation. Just as a recap, we said that evaporation is the change from water at the terrestrial system to the atmosphere, and it could go via plants, like here showed for the transpiration process, or just free water evaporation, either from the interception storage, for instance, on the canopy here, or evaporation from the soil directly. We looked at different evaporation processes: open water evaporation, interception, and evaporation from the soil, as I said before. We defined transpiration, which is a process where the water is leaving through the plant, so the stomata. And we also defined that some term called evapotranspiration, again, a term that I don't like too much. It's a sum of all evaporation fluxes, and I will come to a potential actual evaporation just in a few minutes from now. I think we don't need to go into the processes. Well, maybe the most important, this is a cut through a leaf, and we said very clearly we have 100% humidity or high vapor pressure in this pore, in that stomata at the leaf. Outside we have a vapor pressure deficit, larger one, a lower vapor pressure, and while letting the carbon in, the main reason for the stomata opening is to let the carbon in and fix it here through photosynthesis processes. While doing that, there is some loss of water through this stomata. Yeah, but the main reason for the plants is to open because of assimilating carbon. Good. I think we looked at that figure. Let's look at the daily fluctuations of the energy balance components. Here you see the energy flux in watt per square meter, and the hours during a day. Before 6 o'clock it's night, and after 6 p.m. it's also dark. With the increase of the net radiation at sunrise, what you see here, then the maximum of the net radiation during noon or early afternoon. This is then reflected in a transfer of that net radiation at the one hand to a sensible heat flux. That's the filled squares here. You see a maximum. It's roughly following more or less the net radiation, which is measured at this site and going down in the evening again. And you see also evaporation fluxes from the vegetation. So what we said, it's transpiration. And you see these are the open symbols here with a maximum in the early afternoon here, and going down again. And you see a nice daily fluctuation of these energy balance parameters. A few challenges connected to transpiration. First, it is very different for different plants. Yeah? Plants, in particular in dry environments, they adapted in such a way that they try to minimize the transpiration, also the loss of water, and in dry lands they don't want to get too quickly under water stress. Therefore, they have different strategies to minimize that. One strategy is to leave the leaves. Yeah? So you see in semi-arid climates that some of the plants they leave the leaves, not because of frost or the winter time, what we have here in our humid temperate climate, but it's an effect to lose the leaves, to not lose too much water through the transpiration process. And also here in our climate, different plants transpire at different rates. The density and the geometry of the stomata is very important, and the canopy. You can imagine what kind of canopy you have, what structure you have, how this is set up. Really enables the plants to lose that water more efficiently or not. There are also a couple of mechanical or biogeochemical controls, and there are a number of environmental feedbacks. The solar irradiance, or the incoming radiation, obviously is very important. The air temperature is important. Talked about sensible heat before. The water vapor pressure deficit. What is that again? Vapor pressure deficit? Do we have a vapor pressure deficit in this room at the moment? We always have to ask some questions after lunch. I know it's very difficult to sit in this dark room after lunch. Do we have a water vapor pressure deficit here in this room? What do you think? Yes? Who wants to explain it again? Could we have evaporation at this moment? Yes. I think I'm evaporating also. You know, I'm sweating here while I was standing here in front of you, and losing some moisture maybe, and that's because maybe the humidity in this room is some 70-80% maximum, I would think. Soil moisture. Why does it depend on soil moisture? Because the plants have to take up the soil moisture through the roots, through the fine roots, transport it through the plant, and then lose it. So depending on the availability of moisture, you have an impact on the transpiration. And then also depending on the carbon dioxide. Carbon dioxide is taking up for photosynthesis. That's what green plants are doing. And if we have a different carbon dioxide concentration, you have a different gradient for the plants to open the stomata, and a different efficiency also in carbon assimilation, and also in then the contrary in losing water vapor. Yeah. So what do you think? What do you think if we currently the carbon dioxide concentration in the atmosphere is going very rapidly? Now we are almost at 400 ppm. Before the industrial time, it was less than 280 or something. Now it's growing up rapidly. Of course, it was changing over the last in geologic timescales very significantly. But the last 150 years since industrialization, it's increasing through all the burning of fossil fuel. What do you think? What does that mean for transpiration? If everything else would remain the same, have more or less transpiration? Less. Why? Why do you think less? Who said less? Yeah, the stomata maybe need to not to open so frequently, or not so wide, or not so long during the day, because it can fix enough carbon in shorter times, or in a more efficient way if there's more carbon in the atmosphere. So the trees or the plants get fatter more quickly also through this carbon increase in the atmosphere, and maybe even less transpiration. How that really functions from plant to plant is highly different, but in generally I think the colleague explained it well. Now, evapotranspiration, again, that term which I don't like too much. It's a combination of evaporation and transpiration. There we distinguish between potential evapotranspiration. There's a theoretical rate of ET when all surfaces have unlimited water supply. Yeah? So there's no water shortage, and the transpiration, evaporation is as their maximum fluxes. Depends on the albedo, of course, and on meteorological parameters and the vegetation. What kind of meteorological parameters play a role here? I think incoming radiation I hear somewhere. Yeah, maybe temperature. What do you think of wind? Could that play a role? Yeah. Vapor pressure deficit, the humidity plays a role, etc. Yeah. And vegetation itself. Now the actual evaporation or actual evapotranspiration is the true evapotranspiration, which depends on the soil water availability. As long as there is enough soil water, the actual and the potential evapotranspiration are the same. If there is a limitation on soil moisture, then the actual evapotranspiration is lower, because there's a water stress. Plants or evaporation cannot happen as at most effective rate. Therefore, you have a reduction. So it depends on the plant, soil, and soil water properties, how much they can store soil moisture and how much they can provide soil moisture available then for evapotranspiration. What is often done in practice, you estimate the potential evapotranspiration for a given land use. Open water is one of them, or a 12 centimeter large grass cover. Yeah, and then you adjust that with a crop factor. You say you know the evaporation for a standardized grass, and you know that your forest during this month has a potential ET rate which is, for instance, 10% higher, or these crops have a 10% lower, could be whatever, and then you adjust that with a so-called crop coefficient. Okay, and there are tables for these crop coefficients. We'll look at them later. Another term which you should be aware of is the so-called consumptive use. The consumptive use is a term which is used a lot in agricultural hydrology or in land water development, irrigation, engineering, etc. And that's an irrigation term which describes the actual, often the seasonal consumption. Consumption means consumed by the plants, by the crops usually when you talk about irrigation. So let's look at some value of the potential ET for open water. Tropical regions we have to 1.5 to 3 meters. Potential ET could even be more, but this is kind of a high value already. Mediterranean. We have a rainfall of 2,500 meters, while in Iraq, in a desert environment, some 150 millimeters, and in the Netherlands, maybe 750 to 800 millimeters per year. While the open water evaporation in Singapore is in the order of 1.5 meter, potential evaporation, depending on which land use now, is in the order of 1,400 millimeters, and the actual is just a little bit lower. If you have a seasonality that sometimes not all water can evaporate that the atmosphere demands, then you have a little bit of reduction. In an arid climate, of course, is the opposite. Here, the potential ET is much, much higher. Open water is 2,250, but the potential ET is then 1,800 millimeters, while the actual is only 100. Why does it have to be always less than 150? Because the annual rainfall is only 150 millimeter, long-term average. So long-term, if everything would evaporate, then it would be 150, but the actual is only 100. That means under this climate, we still assume sun runoff generation. Yeah. You see here some numbers for the Netherlands in this table. Is that clear? Potential, actual evaporation? Looks like. Good. Now you have another figure. Here we have 1 and time. 1 means 100%, but the actual equals the potential evaporation. If we go on in time and let a piece of land dry, then there is a reduction from the actual versus the potential evaporation, and the reduction for bare soil is much faster than for cropped surfaces. Why is that like this? Why is the cropped surface, where we have like a piece of land where we have some crops, why is the potential evaporation longer equal to the actual evaporation, while then only the actual evaporation is reduced after some time? While in bare soil it's already reduced much earlier. Why is it like this? Okay. Speak a bit louder, yes? Moisture is taken up by the crops for the cropland, yeah, and here it's already evaporated, and then the surface gets drier and drier, therefore the actual evaporation reduces, while in the crop soils the surface might also be dried out at this point in time, but then the crops still take up water from deeper parts of the soil. Yeah? And they take up the water there and then evaporate again. Therefore we have a longer, higher actual evaporation than on bare land. Is that clear? Good. Thank you for an explanation, sir. I spoke about the crop factor before. You have a reference evaporation, and then you have tabulated KC values, crop factor values for computing for different land surfaces. As a reference ET, often we use the open water evaporation, and then you can calculate from this the evaporation of your forest or cropland or whatever you have. Sometimes also potential evaporation of grassland is used, and then you have other crop factors. In the Netherlands, we have estimated crop factors in this order of magnitude for different periods of the year. Again, these tables you can look up in any hydrology textbook. Clear so far? Potential, actual evaporation? Very good. Then I would like to look a little bit on the terminology of processes when it comes to rainfall. So far we spoke about precipitation, but as soon as we have vegetation involved, we have other rainfall components. we said some of that rainfall is hitting the canopy. Yeah, that's what we call interception. Yeah, some water is then stored here in the canopy storage that can then be saturated, or some evaporation can happen from the canopy. We call that EI, the interception evaporation. Some water from here also falls through. That's the through fall. It maybe hits a leaf, but it's not remaining on that leaf. It falls down. We look at some pictures soon. Yeah. And that's the so-called canopy through fall. Yeah. This rainfall falling here is not interacting with the canopy at all, so it's falling directly to the ground, while this one is hitting the canopy, but not staying there, but falling through. Some of the water is also stored at the canopy, but the canopy cannot store. So-called canopy saturation is exceeded, and then you have a stem flow. The water is traveling down here along the stem down to the ground. Yeah, that's what we call stem flow. While reaching the ground, it could also be stored in a litter surface here. We have some litter evaporation, litter interception, litter evaporation before it goes into the real soil, and then either evaporate from there or do other interesting hydrological processes. So please know the direct throughfall, canopy throughfall, and the stem flow. What do you think is the difference between direct throughfall and canopy throughfall? Is there any difference in the rainfall intensity, in the chemistry of the water? Yeah? Okay. Well, what do you think is different? Yeah. 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 Okay.
It comes down slower, so infiltration capacity isn't exceeded as easily as direct.
Yeah. Very good. Thank you. Everybody agrees with him? You explained it so nicely. It must be true, huh? Yeah. Okay. I agree, and most of the times. But locally, it can even happen that you have a concentration, a channelization of water. I'll show you some pictures in a minute, that you have locally even increased intensity on one local spot here. But generally, some water is stored in the canopy, taking away from the gross rainfall. Therefore, you have a lower rainfall intensity per event. Huh? If you have maybe 20 millimeters rainfall falling here, maybe only 18 millimeters or so are as canopy throughfall, because 2 millimeters are kept in the canopy storage and evaporate from there. And maybe some of the water, as he explained, also travels down the tree and as stem flow. Therefore, it's also not hitting the ground here directly. Yeah. Chemistry, somebody has an opinion on that or an idea what could happen? Do you expect different chemistry for throughfall and direct throughfall? Think about it. We come to it again. Here's the terminology for you to read again carefully at home. More terminology, but I use this by explaining it. I don't want to. I think it's too tiring if I just read out all these sentences. But study them carefully at home. And as it always is in science, it's very important that you use the right terminology. Yeah. So call something canopy throughfall if you mean canopy throughfall. Yeah? So be careful with the terminology, and I try to define them properly here. Look at some throughfall percentages. Now you have two different watersheds or measurements of throughfall. We have a storm size of from 0 up to 150 millimeters, which is a lot of rain. Let's look at the 50 millimeter storm, which is quite a significant storm. Here you have throughfall in the order of 85%. Yeah. If you have a 100 millimeter storm, you have throughfall in the order of almost 90% here. Huh? Yeah, the larger the storm, the higher the throughfall. That's the first thing we learned from this figure. It's clear, if you have a very small rainfall event, then of course more is less to the canopy storage, to the interception storage, and then the throughfall rates become lower. And then you have another watershed which has higher throughfall than this one. Huh? On what could that depend? That for the same rainstorm, 50 millimeter, you have in this watershed 92, and here only 85% throughfall. What could be the reason for this? Different canopy, yeah, different vegetation. Huh? Exactly. Good. Briefly about interception of solid precipitation. Here you see a nice picture from a snowed forest. You see spruce trees, and you see how much water can be stored on these trees. Huh? Sometimes you have in conifer trees you have several centimeters or decimeters of snow stored on the trees. Huh? If you melt all that water, it can be really several millimeters, more than 10 millimeters. Yeah, there's a lot of water that can be stored on these trees. Just sitting there and waiting for melt. And wind, of course, also blows the snow down then. Interception is generally a very important process. I quoted Professor Savenige, the professor of hydrology from TU Delft, last lecture, when I said he hates the term evapotranspiration. He even has published a paper saying why evapotranspiration is wrong. It's a wrong term because at the end it's evaporation. So he really doesn't like that term at all. I introduce it because it's the term used in many textbooks. But I also agree with Huub that we should say total evaporation. And he has another interesting saying is that Cinderella is you know the story about Cinderella, huh? The fairy tale. Yeah. Who is Cinderella? That's this beautiful little girl. Nobody sees how beautiful she is. Yeah. Boys, you look carefully to Cinderella. Yeah. And that's the same like interception in hydrology. It's a very important, a beautiful process, but hardly anybody studies it. So it's not. People don't see how important and how beautiful that process is. So it's the Cinderella of hydrology, he says. And I agree with him. Yeah. Because some 10 to 50% of gross rainfall can be intercepted. Yeah. That's really important. Many hydrologists, they're not interested. This is a bit of water stored on the vegetation or on the topsoil. Yeah, that's not interesting. But can be very important. Yeah. Can have very large variations. Yeah. Can vary a lot for short periods. Small storm events can completely go into interception storage. So 100% is intercepted. Yeah. Highly depend on rainfall frequency. It can reduce the rainfall intensity, as the gentleman just explained, yeah. But locally it can also increase through channelization of the throughfall. We look at a picture in a minute. And it can be a very significant soil water storage and loss even sometimes in snow-dominated system. I think the last picture is justifying that statement. Yeah. So it's a Cinderella of hydrology. Don't underestimate the beauty of this lady. Yeah? Usually, people also say interception is a loss, yeah. But in a cycle, and I think I stressed very much in the first lectures that the water cycle is a real cycle. Huh? There's no loss out of the cycle. That would mean that the water disappears from Earth. So no, there is not a loss. It's just it's going somewhere else. From a catchment point of view, you can say, well, it's a loss that it's not participating in infiltration, runoff generation, groundwater recharge, and these type of processes. But it's not a loss if you look at the water cycle. Please be careful with the term loss. And I hate it if some engineering hydrologists say, well, interception is a loss. We just subtract 10% of the rainfall. So it's a bit too simple, I feel. It can be reduce the input to the terrestrial system. I think I made that clear. It can also reduce transpiration depending on if you have forest or grassland. Yeah? More forest means more interception and also transpiration in general. Throughfall chemistry, I asked about chemistry before. Now you had enough time to think about it. Yes, the interception of the water interacting with the canopy can change the quality of the water. You have some dry deposition on these leaves. These are dust, salt, etc., that is deposited on the top of the leaves or on the leaves, and then while water is sitting there, it's interacting with them, and maybe has a different chemistry than the water that goes down directly via direct throughfall. Yeah, so it can have an increase of some of these anions and cations. Yeah, you can also have leaching from leaves, so washing out of organic carbon, for instance, or potassium. So it changes also the chemistry of the water. And it has some impact on biological processes. So therefore, interception, don't call it just a loss. It's changing the chemistry, it's changing the rainfall rates, it's changing the other evaporation rates. It is really an important process. Here you see some change of the interception during the year. This is deciduous tree in a humid temperate climate, December, January, February, and so on till November again. You see the vegetation period starts here in maybe March, April in particular, and then May, and then you have different leaf cover, different canopy than in the autumn when the trees let the leaves fall. At the moment, it's very beautiful outside. Huh? You see, you have to walk to a forest. Finding forests in the Netherlands is a bit difficult to find, I know, but we have some. If you want to walk to the forest on a Sunday, so it's beautiful at the moment with all these colorful leaves on the forest floor. That's where we are at this moment. It can intercept in coniferous trees up to 25, 35, depends a little bit on how much rainfall we have, of the annual precipitation. So it is a lot. Yeah, it's not just a little factor somewhere. Huh? Deciduous trees usually have much less, 10, 25%, and then it's changing during the seasons. Huh? Here in the summer, you have much more interception losses or interception than during the winter, of course. Yeah. So take that temporal change due to the development of the plants really into account. So therefore, having only just one fixed parameter, a correction factor of 0.9 or something, is just too simple, and it doesn't do justice to this beauty of Cinderella. Yeah. A brief note on stem flow. Stem flow is that water going down the trees. Look at this nice painting here. Because of the geometry of the deciduous trees, you see water is intercepted here, flows along this pathway along the stem, and then goes down. In a conifer tree, it's really different because you have a shape of the canopy like this. So water is still intercepted here, but instead of flowing towards the stem, it's flowing towards the outer parts of the trees, trunks here, and then it's discharging from there down to the ground. This now also connects to what I said before about the channelization of water. When you have certain areas in a tree or a plant where the flow is concentrated, you can have locally even higher rainfall than next to the tree, huh? Because you have a channelization of the water flow pathways. Yeah? That's happening here, here, but also here on the outer side of a conifer. So if it starts raining and you are next to a forest, under which tree should you stand? Huh? If it's a mixed forest, maybe at the beginning it doesn't matter, but you can also stand here. But if it starts longer and longer, you will get more wet here than there because the shielding effect of the canopy. So it's really that different geometry and structure of the canopy that really causes different stem flow, that's this flow, but also different through fall. Of course, if there's lightning, you better go away from the trees, huh? Because you better lay down and get wet, but don't get hit by lightning. Usually, stem flow. Generally, we talk about a low component. Conifers often less than 1%. Yeah. If you have a smooth bark trees, it can go up to 5%, but it really depends on the tree and the structure of the canopy. I think I explained that sufficiently by now. But it can be an important role for nutrient delivery and nutrient recycling, because by flowing down, you wash out some nutrients and some organic carbon. It's a big pain to measure. I mean, it's very difficult to measure this. Yeah, we look at some devices in a minute. It's difficult to quantify perfectly well. Therefore, people take shortcuts and try to account for it with simple empirical equations. But as scientists, of course, we should measure things properly, but it is not easy. Therefore, I come to my next section, and that's about measurement of evaporation. The first and most simple measurement of evaporation is our water balance equation. Maybe I write it down one more time. The precipitation equals the runoff plus the evaporation plus ds dt, storage change per time step. And the simplest is, if you can, long-term averages, maybe you can assume that the ds dt is 0. then you just solve this water balance equation. Now, that's the easiest thing to estimate evaporation. But that means you need to have a very accurate measurement of the rainfall and the runoff. Then you can do it like this. Other things are micrometeorological measurements, where you solve the energy balance equation and then compute the latent heat flux. Or you have empirical physical formula that help you with some parameters like wind, humidity, temperature, incoming radiation, etc., to make a calculation of the evaporation. But that's a calculation. Real measurements really requires the measurements of the energy balance parameters. Then we have evaporation pans. We look at the pictures in a minute. There you daily measure the evaporation out of a pan, and then you can measure the open water evaporation. And with some pan coefficient, that's the Kp in this formula, you can estimate the real open water evaporation. Or lysimeters. Lysimeters are tanks that are buried in the ground. And then sometimes they have a weighing system or a percolation system. We look at some pictures in a minute. And then you can also estimate the evaporation out of that tank. Let's start simple with an evaporation pan. This is the so-called evaporation pan, the so-called Class A pan. Somewhere in the U.S., I think at the U.S. Army Corps of Engineers, they defined the Class A pan like this with these dimensions and say, well, that's the Class A pan. Yeah, it sounds a bit funny. Class A, is there Class B? I'm not aware of a Class B pan actually, but it's a standardized evaporation pan. Yeah, which you have to set up properly. You see here, it's putting on some wood or something so that it's properly leveled, and then you measure the evaporation out of that pan. Here you see one in practice. It's not the latest picture. Sorry for this. And you see this is filled with clear water, need to be very clean, and then you can get evaporation out of this. Yeah. It depends, of course, how much wind you have blowing over that surface. Why is that so important? Why does wind play a role here? The wind, imagine I explained last time over a lake, it's the same that you have always 100% directly above the surface, you have 100% humidity, you know, or what evaporates. So you need a ventilation factor, like wind, who constantly replaces the atmosphere above the lysimeter with unsaturated air. Otherwise, you don't have evaporation. Huh? If it's already 100% saturated, you wouldn't have evaporation. Yeah. Therefore, you need some wind. Now, it depends on how the wind is blowing over what kind of surface. If you have a very dry surface, yeah, but then some green crops surrounding it, the evaporation pan coefficient could be 0.75. If you have a dry surface directly surrounding it, yeah, maybe you have even to calculate with a larger pan coefficient. Yeah? So accounting even more for this so-called oasis effect. With oasis effect, I mean you have a wet environment surrounding by some sort of drier and different land surface. Yeah. If you have one like you all have seen probably pictures of big dams in the desert, like the Aswan Dam in the desert of Sudan and Egypt, and it's a big evaporation pan, you could say. The water is stored in the middle of the desert, surrounded by very dry environment where hardly any water is available for evaporation. So all the incoming energy to that lake is as much as can transferred to evaporation. But if you say, well, the open water evaporation is exactly like the evaporation in this dry lake in the middle of the desert, then you would completely overestimate evaporation because you have this oasis effect, like one wet spot surrounded by a lot of dry atmosphere around it. Yeah? And you constantly replace the air above the evaporation surface with very unsaturated, very dry areas. That's the so-called oasis effect. Therefore, you always have a evaporation pan coefficient of less than 1. Some other pictures of Class A pan. Yeah, you see here, nice steel, clean. I visit the evaporation pan of one of my PhD students. I don't mention a name and a country now. And I visited, and it looked terrible. It was completely dirty. It was algae growing in there, and the water was not clean and not really as dry as you would like to see it. It's not only that, you know, I'm a German professor and everything needs to be clean. Yeah, no, that's not the reason. What do you think is the problem if this water is dirty and full of algae and rather brownish instead of crystal clear? Would you underestimate or overestimate the evaporation? Underestimate. Why? Brown water, why would that be different? Or the albedo is different. So it would reflect more or less brown water compared to clear water. It reflects less, therefore absorbs more energy and transforms more water. So it can even have more evaporation out of it if you have brown water instead of crystal clear water. Yeah? Clear? And then it was not only full of algae, it was a fuel of you know, other, maybe some birds or animals or whatever, you know, happened. And then you have different chemistry, salt concentrations higher, and that might also change the evaporation. So keep the thing clean and dry and clean it regularly. You can also have evaporation pans on floats. This is on a lake in Germany somewhere, where people were measuring lake evaporation, and they had a floating on this reservoir here, and were measuring the water table fluctuations here, and then could measure the evaporation as lake evaporation, yeah, in a nice float. How would you calculate that? I think you can make that calculation very quickly, but in general, the evaporation is the precipitation minus the change of water level. And then if it's 50 millimeters of rainfall, 10 millimeters of change in the water level, then you can estimate evaporation is 15 millimeters. To transfer the measurement of class A pan to the land surface, you then work with the so-called pan coefficient, which is below 1, usually 0.7 something, but it can vary in this range of 0.35 and 0.85. Yeah. Why is it not above 1? What did I just explain? Why is the pan coefficient below 1 and not above 1? You know, you multiply the pan coefficient with your measurement. Yes, because, yes, the evaporation pan, I'm just repeating his words that everybody can hear, that it is a wet environment surrounded by somewhat drier environments, and there's always a sort of oasis effect surrounding it, and you overestimate the evaporation with this instrument. Therefore, you need to account for this by multiplying this with the pan coefficient. Some other instrument, this is a weighing system according to Mr. Wild. Yeah, he put some water here, and this is a very fine scale weight, which you can measure then the mass changes, and the mass changes are recorded and can be interpreted as evaporation. Here you have an even larger oasis effect because you have one you know, wet environment surrounding something drier usually. This is a Pichet evaporimeter. Oh, there's an accent aigu missing. I think Pichet with a little accent here. Doesn't matter. And here you have a column filled with water, and in this column of water you have a porous media here at the bottom. And evaporation is going down is leaving here via this porous media. Yeah. And you put these evaporimeters, you can hang them somewhere in a tree or so, and then the evaporation out of this column of water is then measured by reading how much water is going out of this, and that gives you an evaporation estimate. Now let's look at the lysimeter. A lysimeter is, I said, is a tank buried in the ground. You see here, this is a tank. Here you have even some vegetation in that. You know exactly how deep it is. Could be some few meters. Yeah, it could also be more shallow. And you have maybe a water table. It does not need to be. It can also be completely unsaturated. And then you measure the change of the water table or the moisture change in this tank of water, and that can only get recharged through rainfall, precipitation, or lose water through via evaporation. And to measure that continuously, you can weigh the system. You put it on a scale, but then you need a big, quite high quality system. Or you can have a water table, like here. These are two communicating vessels, and therefore, if you read the water table here, you can control the water table in the lysimeter itself, and then by interpreting the changes of water table here, you can interpret how much water goes down to this groundwater and how much water from this groundwater goes up again to the plant and leaves the system. Yeah, that's a so-called lysimeter. I think in one of the excursions you will also visit some of these instruments. Advantages and disadvantages, and then we break for coffee. It's an excellent thing. You know, it's probably the best. It is the best measurement of evaporation under real-world conditions. In particular, if you have a weighted system, weighted lysimeter, but it is experimentally quite an effort. It's quite expensive. You need. It can easily cost quite some few thousands or tens of thousands of euros. But still, it's a point measurement. You have lysimeters. There are very few that are big, up to a few tens of meters, but usually they are, 1 meter diameter or even less. Yeah, so it's still a point measurement. The soil column in that tank is often not undisturbed. Yeah, so you put in artificial soil, which could be different from the soil surrounding it. Yeah, and it is a quite costly, high experimental effort undertaking. Yeah, in particular if you have a weight system. Yeah, which are the best and most useful ones, and it's. Would be nice if you have more of these systems all around the world, yeah? And then with data available. Any question on this lysimeter? Is that clear how this thing is functioning? Yes, please.
So if you have a lysimeter, you would be also measuring
interception. You can measure everything in theory. Yeah. Also, if you have the plants, you can also measure the rainfall reaching the lysimeter, how much rainfall is lost here in the canopy. You can measure interception pretty accurately. Yeah.
But we wouldn't be able to separate those.
If you measure everything, then you can also separate. But we look at some pictures, but easier to understand if we look at some pictures after the break. But in theory, yes, but it's an experimental effort which should not be underestimated. Yeah. Good. Yes, please.
How do you calculate the true fault? Taking this one as an example, the plant area divided by probably compared to a place where the exception of
Yeah. It's nice because this is plastic. It's not a real plant, but looks like a real one. We could measure the rainfall here where I'm standing now, and that's the direct precipitation. Yes? We could measure the rainfall here somewhere. Beneath, below the canopy. But then it would be different if you measure here, or there, or there. You agree, depending on the canopy directly above. Yeah. Therefore, you would need to measure the through-fall below the canopy at several times, yeah, and then somehow average it, get a representative through-fall measurement. Yeah. And the stem flow we would need to measure here at the main stem. Yeah, it's all plastic, but we would try to measure that here directly. We look at some pictures after the break, and then we can measure all three components on a plant. Yes. Okay, maybe time for a 15 minutes break, and then we will continue.